After going through this module, you should be able to visualize the vibrations of linear and bent triatomic molecules and assign the normal modes to irreducible representations. First, an introduction. Diatomic molecules possess only one mode of vibration, that is stretching. Polyatomic molecules have many more bonds, bond angles and torsions, so that there are many more modes of vibration. It is often difficult to visualize these normal modes, and group theory not only helps in determining the modes of vibration, but it also helps in finding out which of these is infrared active. Coming first to the vibrational modes of molecules, vibrations in molecules compose changes in bond lengths and bond angles and dihedral angles. If you have an n atomic molecule, it has 3 n degrees of freedom, because each atom can be described by 3 Cartesian coordinates, and this means that there are 3 n degrees of freedom. 3 out of these are independent degrees of translational motion in the 3 directions. 3 other comprise the rotational motion, and that means that out of the total of 3n minus 6 are vibrational degrees of freedom. However, linear molecules have only 2 rotational degrees of freedom, as we have seen, because rotation about the bond axis is not a rotation at all, and this means because it has 0 moment of inertia, and this leaves 3n minus 5 vibrational degrees of freedom for linear molecules. Now, let us look at the vibrations of 2 triatomic molecules. We will take examples of water. It is a bent triatomic molecule. This molecule has 3 atoms, it is non-linear, and that means it has 3 into 3 minus 6, that is 3 modes of vibration, and there are 2 bonds, so there should be 2 stretching modes. Either the 2 bonds should be stretching at the same time, or one should compress while the other stretches. The first kind of motion is called symmetric stretch, and this is called nu1, and the other is the anti-symmetric stretch, and this is given a symbol nu3. There is also one bond angle and hence one bending mode, which is called nu2, and all these are shown in this figure. And you see nu1 is a symmetric stretch where both the bonds are stretching at the same time, and it is at a vibrational wave number of 3657 centimeter inverse. The other one is nu2, it is a bending mode, it is at 1595 centimeter inverse, and the third one is at an anti-symmetric stretch. One bond is stretching and the other one is compressing, and this is at 3756 centimeter inverse, and you will note that 1595 centimeter inverse is the bending motion, and it is the lowest frequency, because it is easier to bend a molecule than to stretch its bonds. So, for diatomic molecules, the only mode of vibration has the symmetry sigma g plus. You have seen homonuclear, or sigma plus for heteronuclear, because homonuclear diatomic molecules belong to D infinity H point group, and heteronuclear to C infinity V, where there is no center of symmetry, so no G or U notation. So, we want to see if the normal modes of water also form basis for irreducible representations of the C2V point group, because water belongs to the C2V point group. Let us look at the different symmetry elements. If, as usual, what we do is we put the molecule in a Cartesian frame. The most important axis in this molecule is the C2 axis, which we label as Z. Then the other important axis is the Y axis, and YZ defines the plane of the molecule, and X is perpendicular to the plane of the molecule. So, this is the frame. C2 axis lies along the Z axis, and it is passing through oxygen. The sigma V xz is perpendicular to the plane of the molecule, and sigma V yz is the plane of the molecule. These are 2 planes of symmetry, and there is one rotational axis, and this is the character table of the C2V point group. So, with this convention, this is a convention that we make the most important axis the Z axis, then the least important as X. We find that the first 2 vibrations transform as A1 and the third to B2. Now, look at the result of the C2 operation on nu2 and nu3. So, for nu2, what happens when you perform a C2 operation? Nothing happens, because when you rotate the molecule, the arrows still look similar. So, that means there is no change in the sign of the arrows are pointing in the same direction. But if you do it for nu3, you find that the arrows have now reverse direction. We say that it has reverse direction, so it is -1, the character is -1 for this. For nu2 it is +1, for nu3 it is -1 for C2 operation, and because the arrows have changed direction. The vibrations are labeled with the highest symmetry first, or in the order they appear in the character table. Now that means that you have two A1 modes, one is the symmetric stretch and the other one is the bending mode, and you have one B2 which is the asymmetric or the anti-symmetric stretch. We label them as nu1, nu2, nu3 according to their symmetry. So since A1 is the highest symmetry in the table, character table, the two vibrations, that is the stretching mode, symmetric stretch, and the bending mode, should be labeled as A1. Which one of these is nu1 and which one is nu2? The highest energy one is called nu1, that means that the symmetric stretch will be labeled as nu1, the bending mode as nu2, and nu3 is the antisymmetric stretch. So in the antisymmetric stretch, you can see what is happening. One bond is stretching and the other is compressing. In the other extreme, the other bond is stretching and this one is compressing. So these are the three vibrational modes of water, and you can see that the dipole moment changes during each of these vibrations. In the bending mode, the dipole moment reduces when the bond angle increases, and that is on the left side, and increases when the angle becomes smaller. Hence this mode is also infrared active. In the antisymmetric stretch, the dipole moment vector changes direction from the two-fold axis to the left or right as the molecule vibrates, and thus this mode is also infrared active. Therefore, all three bands should be infrared active, and we have shown the infrared spectrum of liquid water. It is shown in this figure, and you can see that the infrared spectrum of liquid water, it is small peak near 1600 centimeter inverse, corresponds to the bending mode. You had seen that it was around 1595 centimeter inverse, and the broad peak corresponds to the two symmetric stretches which are close in frequency. One is symmetric, the other one is antisymmetric, and you had seen that they are both close to 3700 centimeter inverse. But when you look at the gas phase infrared spectrum of water, you see a lot of rotational fine structure. The gas phase spectrum has many more features. This is because the rotational fine structure is lost in the liquid phase, because what happens in the liquid phase is that the molecules are very close to each other, they cannot undergo free rotation, and they are too close to each other for the rotation to be possible. The rotational fine structure is clearly visible in the bending mode at 1595 centimeter inverse. The CO2 molecule, now we will take another triatomic molecule, but this time it is linear, and this is carbon dioxide. Since it is linear, there are only 5 modes, 2 rotation and 3 translation, which are not vibrational. That means that there are 4 modes of vibration, and these are shown here. The vibrational modes of CO2, one is the symmetric stretching mode, the other one is the asymmetric stretching mode, just like for water molecule, but now you have 2 bendings. Because the molecule is linear, that means there are 2 planes which can be considered perpendicular to this. One is in the plane of the paper, and the other one is perpendicular to the plane. Now carbon dioxide belongs to the D infinity H point group, because it is a linear molecule, and its character table you will see has the E operation, which is do nothing. Then there are C infinity axes, 2 C infinity axes. One is for rotation clockwise by any angle, and the other one is rotation anti-clockwise along the bond axis by any angle. Then there are an infinite number of sigma v planes which pass through all these axes. There is a center of symmetry at the carbon atom. Then there are the improper rotations again by any angle, and then you have NC2 planes also, axes of symmetry. So when you examine the symmetric stretch, we find that under the various operations of the point group, what happens is that when you do E, it does not change. When you rotate it along the bond axis, nothing happens, so it is again 1, and when you reflect it in a plane passing through the internuclear axis, again it looks the same, so again it is 1. When you there is a center of inversion at carbon, the oxygens change position, the arrows will not change direction, they look the same after this operation. So again it is plus 1. In S infinity, what happens, that you rotate by C infinity and then followed by sigma h in a plane perpendicular to this. Again the arrows will look the same, and the C2 also it will look the same, and so it forms a basis for sigma g plus representation. Similarly, the asymmetric stretch transforms as sigma u plus, because it is antisymmetric now. E, it is 1. For C infinity, again the arrows will not change direction. Sigma v also it is the same, but in S infinity it is a rotation by any angle followed by reflection in a plane passing through carbon. So obviously the arrows will change direction, it is minus 1. The same thing happens with I, the same thing happens with the C2, and that means that it is a sigma u plus representation. And the bending modes, they are doubly degenerate, because whether you bend in one plane or a plane which is the other perpendicular for a linear molecule, it does not make any difference. So the energy is the same. It is a doubly degenerate mode, which is pi u. Now, since carbon dioxide is a linear molecule and it is also symmetric, it has no dipole moment, because there is a center of symmetry, it does not have any dipole moment. In the symmetric stretching mode, it maintains the symmetry, because again the carbon oxygen bond lengths remain the same in this mode of vibration. So there is still no dipole moment, and since the symmetry is not broken, the charge distribution remains the same, and this is infrared inactive. Carbon dioxide has two IR active bending modes, the in plane and the out of plane bending of the carbon oxygen bonds. When the molecule bends, the molecule starts resembling water and acquires a dipole moment. This dipole moment is in a direction perpendicular to the bond axis, and this mode is thus infrared active. In the antisymmetric stretch, one bond stretches while the other is compressed, and that means again there will be a dipole moment. There is thus a periodic alteration in the dipole moment, and this vibration mode is also infrared active. So in this table we have shown what happens in the symmetric stretch mode. The molecule maintains its symmetry, its center of inversion, so the dipole moment remains 0. In the bending mode, once it bends downwards and in the other case it bends outwards, it starts looking like water molecule, and then that means it has a dipole moment. And similarly in the asymmetric stretching mode also the same thing happens, that it acquires a dipole moment during each phase of the vibration. Again, the modes are numbered in the same way as for bent molecules. That means that nu1 is the symmetric stretch, nu2 is the bending mode, the doubly degenerate bending mode, and nu3 is the antisymmetric stretch. Carbon dioxide thus has 3 infrared active modes, the 2 bending modes and an antisymmetric stretch. However, since the 2 bending modes are degenerate, only 2 absorptions should be observed. Degenerate means that they have the same energy. So though there may be 2 transitions, you will see only one line. Part of the infrared spectrum of carbon dioxide is shown here, and what you see is that there are 2 bands that we had expected. The peak at 673 centimeter inverse is due to the degenerate bending modes. It is the smallest like you saw for water, but here it is even smaller. The one at 2350 centimeter inverse corresponds to the antisymmetric stretching mode. The small peaks at high wave number are due to combination bands, that is simultaneous excitation of 2 or more vibrations. Just like you had the overtones, you can have combination bands. You can stretch you can excite 2 modes simultaneously. These peaks have a distinctive shape, and it is the PR contour that we have already discussed before, which was encountered for diatomic molecules. It is seen here also because this is a linear molecule like diatomic molecules. In fact, this is a characteristic of all linear molecules. The appearance of a PR contour in the IR spectrum of a molecule confirms that the molecule is linear. You will not find this kind of PR contour for nonlinear molecules, for example for water. The contour of the bending mode is also distinctive. It is different, and this is called a PQR contour. We have already stated that the dipole moment change for this mode is perpendicular to the bond axis, because now it is like the C2 axis of water, which is perpendicular to the bond axis of carbon dioxide. Such modes are called perpendicular modes as opposed to parallel modes, where the dipole moment change is parallel to the bond axis, such as the antisymmetric stretching mode. The rotational selection rule also differ for the two modes. For the perpendicular mode, the selection rule is delta j is equal to 0 plus minus 1. First time we are finding that delta j can be 0, that is, we can observe a pure vibrational transition without any accompanying rotational energy change, whereas for parallel modes, the selection rule is delta j is equal to plus minus 1, that is, a vibrational transition has to be accompanied by a rotational transition. For the fundamental V is equal to 0 to 1 transition, the transition wave number is given by nu bar spectral is equal to S for V j prime minus S0 for V j double prime, and you substitute all these expressions. Since j prime is equal to j double prime, this is equal to omega 0 into 1 minus 2 xc, omega e into 1 minus 2 xc, which is equal to omega 0. You see a pure vibrational transition without any rotational energy change, and here we have substituted j prime is equal to j double prime, V prime is equal to 1 and V double prime is equal to 0. It is the fundamental transition, and in the expression for the rotational and vibrational terms. This equation is valid for all j values. Thus, the Q branch you expect to consist of coincident lines at the band center, and we expect a very intense line at the band center. However, as we have shown in figure, the Q branch appears slightly tilted as a somewhat broad absorption centered around omega 0. So, this is the PQR band contour where you have a very strong central line and then you have a distinctive PR contour. This is due to the difference in the rotational constants for the ground and excited vibration levels, about which we have already learned. On writing B prime and B double prime respectively for the two rotational constants, you can modify this equation that the spectral line wave number is equal to omega 0 plus B prime minus B double prime into j double prime plus 1. The second term is slightly negative since B double prime is smaller than B prime and increases with increasing j double prime. This explains the slight shift to the left with increasing j double prime. In summary, the infrared spectrum of carbon dioxide shows two bands, one bending mode at 667 centimeter inverse with a PQR contour and another at 2350 centimeter inverse, which shows a PR contour corresponding to the asymmetric stretch motion. We may now define normal modes as independent. We have added more definitions to the definition of normal mode. Normal modes can be defined as independent harmonic vibrations which firstly leave the center of mass unmoved, two involve all atoms moving in phase coherent motion, and third transform as an irreducible representation of the molecular point group. And now we will summarize this module. In summary, the number of modes of vibration is 3n minus 6 for bent molecules and 3n minus 5 for linear molecules. Bending modes occur at lower frequency. The modes of vibration are basis for the irreducible representations of the point group of the molecule. And finally, for linear molecules, parallel modes display a PR contour in the rotation vibration spectra, and perpendicular modes display a PQR contour.